Swayam Prabha. Digital India. Educated India.
Hello and welcome again. We continue with our lectures on computer-aided engineering design. We continue with our discussion on B-spline curves and segments. This is lecture number 20. Today we'll discuss B-spline basis functions and how to construct them. What did we do in the previous lecture? Well, we studied the construction or generation of a cubic polynomial spline, phi t. We also talked about what knots are, ti and ti plus 1. And to construct cubic polynomial splines, we had the vertical heights of the splines at each knot. That means the pair ti and yi were available to us. The index I was going from 0 to n minus 1. Recall how we constructed the cubic polynomial spline. We did that as piecewise continuous curve, which was twice differentiable throughout the definition of domain. That is, the cubic piecewise continuous spline was differentiable in the entire range of t. Anyhow, so these are individual segments of that piecewise continuous curve. What is known to us is phi I at ti equals yi, and phi I at ti plus 1 equals yi plus 1. Once again, I is going from 0 to n minus 1. We also had n plus 1 unknown slopes at each pair ti, yi. Those slopes were s0, s1, s2 up till sn. And then we had n minus 1 equations that related these slopes. These equations were of the form si minus 1 over hi minus 1 plus 2 times si within parenthesis 1 over hi minus 1 plus 1 over hi plus si plus 1 over hi equals 3 times yi plus 1 over hi squared plus 3 times yi times within parenthesis 1 over hi minus 1 squared minus 1 over hi squared minus 3 times yi minus 1 over hi minus 1 the whole square. The index I went from 1 up till n minus 1. Hi here was defined as the difference between the two knots ti plus 1 and ti. This was a familiar equation that we had encountered when discussing C2 composite Ferguson curves. If you would recall, this is a tri-diagonal system, and that can be solved very efficiently. But anyhow, to be able to find these intermediate slopes for the cubic polynomial spline to be twice differentiable everywhere, we needed 2 additional conditions. Overall, n plus 1 data points and 2 conditions, that is, n plus 3 conditions were needed to completely determine the spline with n knot spans. In other words, n plus 1 knots. you would have observed how intricate or how involved the mathematics was in the previous. What we will try to do is we will try to construct a B-spline basis function via a polynomial spline. Essentially, we will try to construct this bell-shaped curve, which we call a B-spline basis function. Notice the end conditions here. The value of the spline would be 0 at these two ends. The slope may also be 0 at these two ends. And we can also think of making the curvature also 0 at the two ends. Let's start with these conditions. That is, phi t, phi prime t, and phi double prime t. In other words, the position, slope, and the second derivative of the spline, the piecewise composite continuous spline. Let these be all 0 at each end. How many conditions do you think there will be? Well, 3 plus 3. In all, 6 conditions. We had just seen that we require n plus 3 conditions to completely determine a polynomial spline. Here n is the number of knot spans, for which there would be n plus 1 knots in total. Well, let's try to compare that we require n plus 3 conditions and we already have 6 conditions. That means n would be 3. 6 minus 3. We would require a minimum of 3 knot spans to try to construct this bell-shaped curve. Well, since we have 3 knot spans, we'll have 4 knots. Let these knots be denoted by T I minus 3, T I minus 2, T I minus 1, and Ti. Again, arranged in ascending order. So Ti would be a knot corresponding to this point here. Ti minus 3 would be a knot corresponding to this point here. And Ti minus 2 and Ti minus 1 would be intermediate knots. Remember that we would know the values of the knots beforehand, before attempting to construct the B-spline basis function. So this is the parameter axis, the t-axis, and this is the spline axis, or the phi axis. We plot Ti minus 3, Ti minus 2, Ti minus 1, and Ti as 4 knots. The idea is to be able to construct this bell-shaped curve. We would know possibly the value at this point and the value at this point, but we'll try to figure that later. We may or may not need those values for now. So I had told you earlier that this bell-shaped curve is a piecewise composite spline curve. The first segment is phi sub 0 t. The second segment is phi sub 1 t. And the third segment is phi sub 2 t. Each segment will be standing over a single knot span. All we need to do is figure what phi 0, phi 1, and phi 2 are. We start with the conditions that are given to us. The position, slope, and the second derivative, they are all 0 here. And likewise, the position, slope, and the second derivative here are all 0. With these 6 conditions and 3 knot spans, we should be able to uniquely determine what phi 0, phi 1 and phi 2 would be. Now the question is, what do you think would be a solution? You might want to take a moment. If you come up with an answer saying that the trivial solution will be phi equals 0, in other words, phi 0 is 0, phi 1 is 0 and phi 2 is 0, then I would say that you are correct. What do we do now? We can try exercising a few options. One of the options can be that we can introduce another condition, and when doing that, we'll have to introduce another knot. Let's see what happens. Let's introduce another knot to the left, Ti minus 4. A word first about how I try to compute and construct B-spline basis functions. I like to go from right to left. There are many books that would go from left to right, but it doesn't matter. I'm comfortable with going from right to left. Anyhow, coming back to our discussion, we have introduced another knot and therefore another knot span. So now we have 4 knot spans. Ti minus 4 to Ti minus 3 is 1, Ti minus 3 to Ti minus 2 is the second, Ti minus 2 to Ti minus 1 the third, and Ti minus 1 to Ti the fourth. Now let's try to construct a cubic basis spline over the 4 knot spans. Here n is equal to 4 and the knot span spans from Ti minus 4 to Ti. We have seen before that if I had introduced another knot or another knot span, I would require one more condition in addition to the 6 conditions that we had before. Why do we need one additional condition? Well, recall that we have n plus 3 unknowns present overall, where n would be the number of knot spans. We use something called the standardizing condition to ensure that this B-spline basis function is not 0 in between the values Ti minus 4 to Ti. We ensure that the area under this spline curve is non-zero. That is, integral from Ti minus m to Ti of phi of t dt is equal to 1 over m. Here, m is the order of the curve. Remember, m minus 1 would be the degree of the curve. So in this case, this is a cubic spline for which m equals 4. Now, if I go leftward from Ti, the first knot that I'll have will be Ti minus 4. If this is a curve of order m, this knot here can be generalized to Ti minus m, which is this value here. We have seen that the area under the curve is non-zero, so that the polynomial spline is non-zero in between the values Ti minus 4, and Ti. We call this a fundamental spline. And I'll tell you the reason why we call this a fundamental spline a little later. Let's take a look at an example. We try to construct a standard cubic, again, piecewise continuous composite spline over the knot span Ti equals I, where I goes from 0 to 4. We understand that the placement of these knots is uniform. The boundary conditions will be symmetric. So our standardized spline will be symmetric about t equals 2. This would mean that we would need to compute only 2 segments of the spline, phi 0t in the knot span 0, 1 and phi 1t in the knot span 1, 2. Since each polynomial segment is cubic, we can write phi 0t as a0 plus a1t plus a2t squared plus a3t cubed. a0, a1, a2, and a3 are unknown coefficients that we need to determine. Let's start with the boundary conditions on the left. Position, slope, and second derivative are 0. This would mean that a0, a1, and a2 are all 0. And so we can write phi 0t as simply a3 times t cubed. A3 is still an unknown. Now, phi 1 being also cubic, we can write phi 1 as b0 plus b1t plus b2t squared plus b3t cubed, where now b0, b1, b2, and b3 are unknowns. How do we find them? All we need to do is ensure position, slope, and the continuity in second derivative at the junction point t equals 1. Recall the basic definition of spline. An n degree curve has to be n minus 1 continuous throughout the domain of definition. So a cubic spline has to be C2 continuous throughout. Therefore, at the junction point T1 equals 1, we'll have to have phi 0 at 1 equals phi 1 at 1, position continuity, phi prime 0 at 1 equals phi prime of 1 at 1, slope continuity, and phi double prime 0 at 1 equals phi double prime of 1 at 1, the continuity in the second derivative. Correspondingly, we'll get 3 equations. b0 plus b1 plus b2 plus b3 equals a3. b1 plus 2 times b2 plus 3 times b3 equals 3 times a3. 2b2 plus 6b3 equals 6a3. So far the story is that a3 is not known to us. b0, b1, b2, and b3 are also not known to us. And then we have these 3 equations. We can eliminate some of the unknowns over here. We can write b0, b1, and b2 in terms of b3, which would make phi 1 of t as a3 minus b3 minus 3 times a3 minus b3 times t plus 3 times a3 minus b3 times t squared plus b3 times t cubed. Now what? Now we have B3 as an unknown and A3 also as an unknown. We need to figure these two unknowns, for which we would need two conditions. Can you think about those two conditions? Let me give you two clues. One, symmetry of the composite spline at t equals 2, and 2, standardization of the spline. Let's use the first condition. The spline is symmetric about t equals 2, which would mean that the slope at that point will be 0. In other words, the first derivative of phi 1 at 2 will be 0. This would generate the condition minus 3 times A3 minus B3 plus 12 times A3 minus B3 plus 12 times B3 equals 0. And this would help us get a relation between A3 and B3. We can express B3 as minus 3 times A3, which would make phi 1 of t as 4 times A3 minus 12 times A3 times t plus 12 times A3 times t squared minus 3 times A3 times t cubed. Now, how do we find A3? Using symmetry, which we have used here, and noting that the order of the curve is 4, we now use the standardization condition. That is, the area of this composite piecewise spline in between the knots 0 and 4 is equal to 1 over 4. Now, since the spline is symmetric, I can write this equation as 2 times integral 0 to 2 phi t dt, which is equal to 2 times integral 0 to 1 phi 0 t dt plus 2 times integral 1 to 2 phi 1 t dt. We have by now acquired the algebraic expressions for phi 0 and phi 1. We can use that and compute the area under the curve as A3 over 2 plus 11 times A3 over 2, which is 6 times A3, which is equal to 1 over m, something that I have mentioned earlier, and m for us is 4. Cubic polynomial composite continuous piecewise. Many terms. Confusing. Okay. So A3 will be 1 over 24. We can substitute for A3 in phi 0 to get phi 0 of t is equal to 1 over 24 times t cubed, and phi 1 of t equals 1 over 24 times 4 minus 12 times t plus 12 times t squared minus 3 times t cubed. Now, how about phi 2 and phi 3? So, phi 2 was a piece of this polynomial spline in the knot span 2 and 3, and phi 3 is a piece in between the knots 3 and 4. We can use symmetry, and we can say that phi of 2 plus delta is the same as phi of 2 minus delta for any delta, which would give us phi 2 of t equals 1 over 24 times 4 minus 12 times 4 minus t plus 12 times 4 minus t squared minus 3 times 4 minus t cubed. All you need to do is plug in 4 minus t in place of t to take care of this transformation. Likewise, phi 3 of t will be 1 over 24, 4 minus t cubed. Phi 3 would be the symmetric part of phi 0, and phi 2 is the symmetric part of phi 1. Let's try to plot these segments and understand how these segments come together and form a composite continuous basis function or spline, specifically a cubic spline in this case. So this is how the entire basis function is going to look like. The knot values are 0, 1, 2, 3, and 4. This red curve here is the first segment. The green one is the second segment. The orange one is the third segment, which is symmetric to the green one. And this segment here is symmetric to the red segment here. This segment here is phi sub 0. This one is phi sub 1. This is phi sub 2. And the last one is phi sub 3. To summarize, we have position, slope, and second derivatives as 0 here and the same as 0 here. At this junction point, we have position, slope, and second derivative continuity. Likewise, for this junction point and for this junction point, position, slope, and continuity in the second derivative. And of course, you would notice that the slope here is 0 because this basis function is symmetric at t equals 2. Now let's try to understand the general form of an order 4 spline. It may or may not be symmetric. The knots may or may not be uniformly placed. I start with ti minus 4. This is ti minus 3, ti minus 2, ti minus 1, and ti. Well, although I have plotted these knots from left to right, I should ideally go from right to left, simply because it's convenient to me. Once again, we have 4 knot spans over which this order 4 composite spline is standing. Let me nomenclate this spline as M sub 4I. The first index corresponds to the order of the spline. The second index corresponds to the last knot over which this spline function stands. This corresponds to ti right here. Further, I do not need to restrict myself to the values of t in between ti minus 4 and ti. I can use the values less than ti minus 4, and also I can use the values greater than ti. Just that this spline M4I will be 0 here and here. The general form in the knot span ti minus 4 equal to smaller than t equal to smaller than ti is this. This general form can be extended indefinitely from ti minus 4 to the left and ti to the right on the t-axis, which is something I had just mentioned. So what will happen is M for I will be standing over an indefinite number of spans, only that it is going to be non-zero for values in between Ti minus 4 and Ti, which are precisely 4 spans, 1, 2, 3, and 4. I had mentioned before that this is called a fundamental spline, or the spline of minimal support. It is the minimum number of spans over which the spline can be non-zero. We'll come to this a little later, but let me emphasize here that these belt-shaped B-spline basis functions have barycentric properties, and that's the reason why they are called basis spline or B-spline polynomials or functions. Although I have been using the term B-spline or basis spline, this is the formal reason why. Let's look at a generalized B-spline or a basis spline. So far, we were able to construct a B-spline function of order 4, that is, of degree 3. It is possible for us to construct in a very similar manner a B-spline function of order m with the last knot as Ti. And if you recall the nomenclature that we had just seen, this nomenclature will be capital M. The first index is small m. The second index is I. Capital M stands for the B-spline. Small m stands for the order of the B-spline. And I stands for the index corresponding to the last knot over which the spline stands. Try to remember how we constructed order 4 B-spline basis function. We can construct a generalized B-spline basis function in a similar manner. That is, mi of t may be computed with the n conditions. Mmit is equal to the first derivative of the function is equal to the second derivative of the function up till the m minus 2th derivative of order m B-spline, and we set all these derivatives as 0. And we do that at both the ends, the end on the left and the right. How many conditions do you think there will be? There would be 2 times m minus 1 conditions. We will have additional conditions as well, and they would correspond to those at the junction points. There would be the continuity conditions, the position, slope, the second derivative, and so on and so forth, up till the m minus 2th derivative. They should all be continuous at the junction points over the interior knots. Once again, go back to the definition of spline. A spline of order m is Cm minus 2, continuous everywhere. We have seen in the previous lecture, and a bit of it today, that computing B-splines as polynomial splines can be a little tedious and can require quite a few algebraic manipulations. And it may not be easy for us to write a computer program to be able to handle that. We should look for better ways to construct B-spline basis functions. One of those ways is the divided differences approach. We will be studying different techniques to synthesize or construct B-spline basis functions later. But let's try to fix the geometry behind all these algebraic manipulations that we'll be doing throughout these lectures. I always emphasize on geometry because this is what makes us all understand things a lot better. Now, this is the way I remember to construct B-spline basis functions. This is a general one of order m. This is my vertical axis or ordinate. This is my parameter axis. Now, let me ask you how you would want to construct a B-spline of order m. Well, as I said, I'll go from right to left. This is my m sub I t. Now, these two indices, they would have information pertaining to the entire knot span here. As I said, this is the parameter axis t. The last knot would correspond to ti, and the first knot would correspond to ti minus m. Okay, so all you would need to do is first, corresponding to this index, plot the last knot, and then use the index and the order to figure what the ti minus nth knot is and plot it on the left. So your generalized order m spline is going to be standing over the knot span ti minus m and ti. Then start plotting the intermediate knots, ti minus m plus 1, ti minus m plus 2, ti minus m plus 3, and so on and so forth up till ti minus 1, and then finally ti, which you have already plotted. You might want to do this exercise a few times to try to fix this geometric method of sketching a B-spline basis function of order m. Once you are comfortable with this, it will be a lot easier for us to understand the material covered in subsequent lectures. Maybe I'll do a few examples for you on the board. How about constructing a B-spline basis function of order 3, and I would represent the last knot as a function of t. Okay. Draw the vertical axis, draw the parameter axis. This is m3 I t. 3 is the order of the spline. That means that the spline would be quadratic. Okay, now step 1. Plot the last knot, ti. Step 2. Figure out the first knot. What do you think that will be? ti minus 3. How about the intermediate knots? We'll have ti minus 2 and then ti minus 1. And your quadratic spline will be standing over these 3 knot spans. It's not very difficult to understand. Let's try a difficult one. M6, say I minus 2, t. You will be constructing many of these spline functions to be able to understand their properties a lot better. Okay, the vertical axis and the parameter axis. This is m 6 I minus 2 t. Okay, can you help me out? What is step 1? Step 1 is to plot again the last knot. This would correspond to t I minus 2. Let me give you a little perspective here. I'll also plot ti and ti minus 1. But this would be the knot which would be important for me at this time. How about the first knot? This would correspond to ti minus 2 minus 6, which is ti minus 8. Let me plot this thing here. Let me not worry about these intermediate knots at this time, and let me go ahead and plot m6 I minus 2 of t. I have deliberately drawn this as an unsymmetric bell-shaped function. I should be careful here. I have to have position, slope, the second derivative, maybe the third derivative, and so on and so forth, all 0. So I cannot have a non-zero slope here. So how about the intermediate knots now? ti minus 7, ti minus 6, ti minus 5, ti minus 4, ti minus 3, and then we have ti minus 2 here. If I ask you to plot over this, m, let's say 5 I minus 1 of t, would you be able to do that? Okay, so our starting knot is ti minus 1, which is this one here. Our first knot is ti minus 1 minus 5, which is ti minus 6, which is this knot here. I'm going to be careful at how I draw the slopes here at the two endpoints. This is m 5 I minus 1 of t. 10 marks for guessing this. Over how many knot spans will this function stand? 1, 2, 3, 4, and 5. The order of the B-spline basis function.